We've got it. All right. Thank you, Brad, and welcome to the October Silicon Valley Fourth Interest Group Zoom meeting. Thank you all for coming. I wanted to get started briefly with a review of the Silicon Valley Fourth Interest Group's functions in this world. Coming up in November is our annual Fourth Day, a long-standing tradition that goes back to the very early days of FIG. I remember starting off, they were always looking for a deal on hotel ballrooms and convention centers. So we occupied the very first meetings at a number of fine Bay Area meeting venues. So there is monthly meeting, and if you missed this monthly meeting, you can go to our YouTube channel and see a number of these monthly meetings. Okay, we have an email list, the administrator of which is service at the moment. So if you're on the email list, you're aware of it. If not, hopefully you can communicate with us in other ways. And there is the website, both the FIG website and Silicon Valley's own website as a subheading off the FIG website that are maintained by our esteemed webmaster, Dave Jaffe. Thank you, Dave. All right, so anybody think of anything else that FIG is doing? Oh yes, I'll be talking later about it's online, all the things that are online. I think there's Hit Peak Primer around somewhere. I have a paper copy somewhere. All right, without further ado, I'd like to hand the floor over to our esteemed Chairman Emeritus, Bill Ragsdale.
Very good. Thank you so much. We're going to have fun today. We're going to do some essentially multimedia, simplistic multimedia here. As I use a thing called X switch, and I can now switch views. As an introduction, looking forward toward the fourth day. Last time we did this, we had the Jeopardy. We had fourth Jeopardy, which had all kinds of fourth historical questions. But we're now soliciting questions for a new Jeopardy this year. So if any of you have interesting, tricky little history snippets of fourth history, please send them in. Kevin's going to post my email address under the chat segment. So they don't necessarily have to be tricky or too clever, mainly just things that are of interest. So it would be like, who did what, when, what force, what was interesting about them, what application, what trip was done, what meeting was held somewhere, anything we can play on in fourth-based topics. Remember, an interesting one would be, in fourth words, the illusions, the tricks, where the fourth words came from, how things changed. Anyway, use your imagination. Let's think of all the little Jeopardy style questions that we can do to build it. Last time I did it probably from a memory bank dump, and I unfortunately dumped my whole memory into that Jeopardy. So that's all we've got. And with that basis, I'll segue into my talk for today. Is that okay, Fearless Leader Kevin? Are we ready for that?
It is certainly okay, and everyone will notice that in the chat is Bill Ragsdale's email address. So please make use of it. If you've got a question now that you can think of, send it direct DM to Bill or send it email to Bill now, preferably email, since we don't want to burden Bill with having to cut and paste from the chat window and it's hard to save and da-da-da-da-da. But don't publish it to everyone, please, because that'll spoil it. Those of us that are here, we want to have your question. We want to experience your question as part of the big Jeopardy game board. So on with the show, Bill.
Very good.
If you've not muted your mic, mute now.
All righty. Joy to be here today. Thank you. At the Silicon Valley Fort Interest Group. The topic today is going to be Along the Fourth Jungle with Gun and Camera. Now, this is a takeoff on travel and adventure books that were in the 1920s and 30s. They would have such things as Along the Zambezi River with Gun and Camera. So it would be a travel story, visiting Nairobi with gun and camera, and so on. So we'll take that same metaphor today to examine a history of fourth applications and fourth technology. So our itinerary for our journey today. This is, of course, my personal journey, which starts as a bumpy road from a one-board 6502 processor, moving through a series of automation projects, control projects, and then 15, 20 years later, ending up with Win32 Fourth. At the end, I'll also do a fairly broad view of the book I've written, Win32 Fourth Guide. So our quest, the company that I started in 1971 with my bride Ann. We had been married 6 months, and I told her I was leaving a secure government job and we were going to start a company. And our entire savings was $28,000. So we bootstrapped the company from $28,000 up. We had enough money to live for the first year, and then after that, we weren't sure what was going to happen. So the company Dorado Systems, we made communication equipment. These days it's called supervisory control or SCADA systems, remote control and monitoring. We got into access control. I'd had some background in that. And we had built for Honeywell Corporation a one-door controller. It was called Memory at the Door. It had a 1,000-person memory in a diode matrix associated with each door. So they could put in a 20-door system, but they had to have 20-door controllers, and each controller had its own memory, all hardwired logic. The next generation was coming along, and we knew we needed something programmable. We didn't really need a computer, but we needed to program the logic. We needed the flexibility and the memory. Now, this was about 1975, and at that time, the 8080 processor that had come out cost $400. In today's money, that's around $1,400. So the programming chip, the 8080, would be in today's money about $1,400. So that presented a series of challenges. So the weapons we use on this journey is first, a processor we'll examine in great detail called the Jolt, which was a little tabletop one board computer system, board computer in 1975. We integrated that Jolt into what we call the blue box. It has no relationship to John Draper's blue box, but it was our tabletop development system. Then we built our own 6502 processor assembly, which went into to a unit called the Brick, which was about a 1-foot cube development system. And then we migrated to F83 by Laxon and Perry on a PC in 1983, and that was our development system thereafter. NC Fourth came along in the mid-80s, and I was on the standards team for that. Our work at Dorado kind of migrated in that direction, but mainly we were focused on F83. And then finally, about the time I retired from the company, the Win32 came along. So the weapons we used on this journey, the first weapon, number one, was the one-board computer called the Jolt. It was $275. This was a full-page ad from Byte magazine. And remember, this was at a time when just the 8080 processor cost about $400. So it took the world by storm. For a one-board computer, it was certainly leading the pack. It had the CPU running at 1 megahertz. On this single board computer, there was enough RAM, 512 bytes of RAM to do the page 0 and page 1, which were essential to that architecture. That was a monitor board. It was variously called either the Demon, debug monitor, TIM, which is terminal interface monitor. It had a 1K ROM that did a lot of support functions, a couple timers, 6 IO lines. So this could be a 2-chip processor with this debug monitor and the CPU. If you added a peripheral interface adapter, you got 16 more IO lines and some more memory, and I think a couple more timers. On board was an RS-232 teletype interface. Baud rate was selectable. When you powered the unit on, you'd hit the letter R on your terminal and it would lock on to what your baud rate was. Interrupts, and then they offered RAM expansion and ROM expansion. So as a little satellite to our excursion here, we're going to stop along the trail, and we'll note that I saw the ad for Byte magazine on this on Wednesday, and it exactly fit a project need we had, which I'll mention in a few moments. So I ordered by telephone on Thursday. The company supplier Microprocessor Associates Incorporated had done their second generation monitor chip was in FedEx heading toward them. They got it on Friday. I went over on Saturday and picked up the board, the kit, and it was hand lettered in India ink on the board, serial number 1. Built it on Sunday, and by Sunday afternoon I ran it. So we had, in a 4-day turnaround, we had the first Jolt system built. There's an interesting play on words. Manny Lemus and Ray Holt were behind this company. Manny Lemus was Hispanic, and he would play the name game on Ray Holt's name. The Spanish J is pronounced like H. Lemus would pronounce Holt's name like a reverse phonetic translation. Instead of Holt, he'd call him Jolt. So he always called him Ray Jolt, and that's why the board is named the Jolt board. They came out with an assembler. They got a local programmer to write an assembler. He did 3 versions of it. I was the beta test. It was buggy. It kept buggy. They redid it a couple times, and the programmer finally quit. And he said, "I've spent all my time, all my money. I'm done with this." So with working with a friend, Bob Seltzer, and I, we disassembled the assembler manually, 2K bytes, rewrote it, coded it, punched it on punch paper tape on an ASR teletype, fixed the bugs, and made one final pass, and we had a patched assembler. It went back to MAI. They made a prom of it, and that became their standard assembler that was support the product. And then we began my 4th journey. So our target number 1, the first game animal we're going to try to target would be a demonstration for Honeywell of an ID badge reader. We had been doing this one-door controller that was hardwired logic, and we wanted to go to magnetic stripe, which did imply much more processing power. So we got a commercially available pass-through card reader, and this is the Jolt board. It's got the CPU, a PIA, and the monitor, and then some glue chips along the way. And we just discussed a moment ago that was designed by Ray Holt and Manny. They also designed the SIM1 for Cinertech, and ultimately they sold their company to Cinertech. And I think they either inspired or designed the KIM-1 that was sold by MOS Technology. I think they had their finger in that pot somehow. So this was the demo project. A simple pass-through reader. The serial data was captured on the Jolt board, a lookup table, and it was done, and the teletype printed the result. Honeywell was thrilled. They had had discussions with 2 other vendors going on that had big problems. And so they were delighted that we, as a continuing vendor, would get the new project. At this point, all of our edits and assembly was done on paper tape. So you take source program in assembler, you type in the code, out comes paper tape. If you make a typing error, you cut the tape, you retype the correction, and you splice it in with ink, with paper and scissors and glue. This was our very start. So the weapons, weapon number 2 came along. Weapon number 2 was FIG-4. Once we had the assembler running and the simple editor, then we used that to write what I call Tooth, T-W-O-T-H. I thought it was about half as good as 4th, and it was a bootstrap system that got me running a 4th-like system. And then we used that to bootstrap FIG-4. We needed a development system. So 4th was created, patterned after, modeled after Micro 4 6800. 4th Inc. had announced, of course, that they were not going to support personal computers. They disdained the hobby aspect of personal computers and realized that there wasn't a lot of money there. They weren't able to do large systems at the price performance level that the personal computer industry would accommodate. So we had kind of an open field running as long as we were not competing directly with 4th Inc. product. So my little 4th called Tooth grew to become FIG-4 over the course of a year or so. And then along came our 4th interest group. And of course, we all know the huge amount of side effort that went into that. Incidentally, here's a picture of me at one of the West Coast computer conferences wearing the good old FIG t-shirt. So our weapon number 3, I mentioned the blue box. Well, the blue box was the Jolt system integrated with a per-side dual floppy drive, a high-speed paper tape reader, and an ADM3A terminal. And all of this was supported by the TIM monitor chip and, of course, by 4th. Per-side had an advantage in that the dual floppy drive was supported with a controller that had an ASCII serial interface. So you could rewrite sectors. And if you go into the FIG model that's published back in those days, you'll actually see the driver that interfaced to the per-side controller. It basically could read a sector and write a sector. Incidentally, the ADM3 terminal, we thought we died and gone to heaven when that came along because we could get rid of the paper tape and teletypes. At this point, 4th was in ROM, so we would just push a reset button on the development system and right away we're into 4th. It's a picture of what went inside the blue box. There is the full expanded Jolt system, which has the CPU on top and the ribbon cable together. In place of a backplane, we have the ROM board, the RAM board, an IO board, and a power supply. And here's our full configuration. And again, miraculously, in their monitor, they had the code for parallel data input from punch paper tape. It would read teletype format tape, but with high-speed paper tape. So we still use paper tape for input as an archival storage up until we got the per-side drive in place. So using this new ammunitions on our trail, we then went in for our second kill. Second kill was a 4-door control panel. It was battery backed up. One panel would be wall mounted in an industrial building and could connect to 4 different doors. Reported to the Honeywell Alpha 3000, which was a small computer-based security system. I shouldn't say small. It would handle large buildings, including airports. We programmed this in subroutine threaded 4th, which was tethered to the brick development system. We had an umbilical cable. We'd pull out the monitor chip from our product, plug in an umbilical cable to our development system, and then it appeared as if the access control panel was a peripheral to our brick development system. This was an immensely successful product. We sold roughly 2,000 of them worldwide. BZR is the German's police central records bureau. We did about 4 nuclear power plants, including San Onofre, San Clemente, the Denver Stapleton Airport, and along the way, about 12 other airports. The fourth was very high performance in this panel. The card reader was a serial card reader with 1 wire out. The magstripe data was serial, with just the flux transitions on the card itself. So you put the card in and you get about 100 transitions coming out. They were accepted in real time as real-time interrupts. The time delta between each transition was recorded and at the interrupt level, and then slower processing would pick apart these time differentials. And the little 16502 could handle 4 simultaneous data streams coming in. So the transient data on that was extremely high at the interrupt level, and it worked beautifully. The only problem we ever had, well, we had a lot of problems, but the big problem that was had, the weird one, was our ID badge only had on it about 60 transitions, so that with all 4 badge readers going together, we had a limited number of transitions, and it would fit within 1 page of a 512 byte or fit within a 256 byte memory page. One day, a customer on a job shoved in an American Express card, and it crashed the system. So this caused great repercussions through our company and through Honeywell. We had a little Project Tiger team. Why did the processor crash? We even called MOS Technology, and I think since we had mentioned the name Honeywell, Chuck Peddle himself called back because he was worried that there might be a software flaw in the processor because it was fairly new. After we did the analysis on it, we found out what happened was we were actually just crashing the stack because we didn't have a proper limitation set on stack entries on interrupts. We put the proper limit on stack depth, and the problem went away. Here's a picture of the controller. The logic board in the center, it is about 8 by 12 inches. And I look at that today and I think that is just amazing because I designed that thing 100%. And I'm wondering if today I could go back and recreate a project like that. The readers on the left, and inside was a very, very simple circuitry because we just translated the flux transitions on the card into a single bit data stream, and all the heavy lifting was done inside the processor board. At the bottom right, there is an interface panel. All of the electrical wiring was isolated by ribbon cable from the main CPU board so that the field installation people did not touch the CPU board. And again, as I said, several thousand of these were sold. So weapon number 4 came along. Weapon number 4 was F-83, written by Henry Laxon and Mike Perry. At this point, we moved to PCs. We retired the brick, and from then on, we were on PCs. Archiving now was done in files, not in blocks. That was a big change. Andrew McEwen was very active at this point. He guided the transition from our brick to the PC world. And we were on hard drives at last. So that was a great step too. Kill number 3. Kill number 3 was a standalone card reader. We took the essential logic out of the panel on the one door and compressed it into a 80C51 processor, which was inside the card reader. And so it would do the data input, the timing analysis, format conversion, and it would output in a industry standard serial protocol. The chip was one-time programmable. The earlier ones were EEPROM and had a window in them so they could be erased. Once we got into production, they took the EEPROM chip and put no window on it. It was a cheaper chip. You would program it one time only. You could do testing, and then when you were happy with it, you could set 1 bit, a fuse link, and then it was no longer readable or programmable from a security standpoint. We sold these industry-wide, not only to Honeywell, but to many other commercial companies. And for example, the largest single job we did was at Denver International Airport. There were 4,000 of them installed there. That was a golden year when we sold 4,000 of these to one job. And a 3rd generation derivative of this is still in use. I sold my company in '95. It went through 2 other handlings, and you can see online derivatives of this are still available to be plug compatible. And if you go on eBay and look under Dorado Systems, you'll actually see some of our old product that's still new old stock sitting on somebody's shelf. So kill number 4 came along. This was called the Cyberknock. We hardly think anything of the name. It's just, what it's called the Cyberknock, and people would raise their eyebrow about that and say, what's that for? What's that name? Well, it turned out the project engineer on this was a young fellow named Nick Avdonin, and his contributions were so strong on this that we wanted to recognize that, so we let him name the product. And he was fond of an underwater superhero that swam that was called the Cyberknock, so he got to name the product as the Cyberknock. It was an energy controller for retail stores. At this time period in the mid-'80s, energy conservation was coming to the forefront, and the power rates in California were rising, even probably more than they are right now. And so a local contractor came to us that had a key customer of Lucky Stores. And Lucky Stores was kind of tearing their hair about refrigeration energy costs, very key to stores still to this day. So this system had an install cost to Lucky Food Stores of about $5,000, with the controller we sold, which is about $1,000, and then all of the installation and field equipment. However, after spending $5,000 install cost, they found that they were saving about $1,000 a month. So the payout time on this was 5 months. And this time in the industry, they were looking for payouts that were in the range of 18 months to 2 years. And Lucky Food Stores did a break even on this in 5 months. Their manager was written up in trade periodicals, and he was designated Energy Manager of the Year in about 1987. So he became a hero both in Lucky Stores and outside. The controller for 24 channels would take on, off, auto, and cycle loads. You could put lighting on it. You could put refrigeration on it. Yeah, you could put parking lot lights on it, and you could set time of day schedules, and you could do cycling. And each channel had several different programming possibilities. The device had a 1200 baud dial-up telephone modem in it. So our customer could take a little break here while I mute my telephone. There we go. The customer had a Texas Instruments Silent 700 terminal that had earmuffs on it, and you could plug your telephone into it and use it to dial directly. So he could, from his office or from his home, 24/7, he could dial up into any one of the Lucky Food Stores. He could do overrides, he could answer problems, and he wrote a simple basic program that would interrogate these sequentially. It would call each store, generate a simple report. So every morning he could come in and he would get a report from the status of each of these stores. In particular, if the store was on override, he would get a report on it. And this was very important because the store people were not in the business of saving energy. They were in the business of selling groceries. So if there was any problem, any complaint anywhere, they just ran to the panel, flipped the switch, and went on to override, and then they forgot about it. So the next morning, he would get the report to say, well, channel 3 on store 57 is on override. They would then check and see what the problem is, and they could know if it was something they had to send service out for or how it could be corrected. So they loved this monitor the store for overrides. The CPU was the Centertech Sim 1. We'll see a shot of that in just a moment. We then added the store interface, a 1200 baud modem, real-time clock, battery backup, and terminal input. And of course, inside this, our hidden weapon was Forth. We could talk to the inside of this controller using Forth. Here's the Sim 1 board. It was designed again by Manny Lemus and Ray Holt, so this is essentially a third generation from the Jolt processor. Fully integrated, it had a LED display, the simple keypad. It again sold for several $100s. We would buy the OEM version that had no display and no keypad. So what we were doing was short-circuiting the development process by getting a board that had all the RAM, ROM, input interface, and then we added the field portion. This is how the Cyberknock would look. Unfortunately, I don't have a photograph of it. Went through all the records and did not find a picture. The SIM board at the bottom right linked to the left to the store interface. This was 24 channels optically isolated because we're controlling a lot of heavy machinery. We're doing 220 volt contactors. We're doing hundreds of horsepower of refrigeration equipment. The line above shows that our interface board had the modem, the clock, diagnostic terminal, and so on. And then at the top left, we see the Silent 700 for TI that was either the on-site or the remote interface. There was an interesting aspect on managing this project. Our contact at the customer was a very experienced field tech engineer, but he had no formal training and did not know how to go about preparing a purchase specification or even a description of his job. His quote was, "I don't know what I want, but I'll know when I see it." So it was our job to interactively show him things. He would then say, change this, add that, move that around, and even, have you thought of this idea? So we met with him about every 3 days. We'd do a review, sitting literally he would sit at the terminal and he would talk to the Forth simulated product, pretend he was running a store. He would say, I want to do this. And if the product didn't do it, we would then write that down, note it down. Next day, we'd come in, rewrite software, add up. A couple of days later, he'd come back and we'd repeat this again. So we went through this loop numerous times. And after about 6 weeks, he said, that's perfect, let's ship it. So I've written in Forth the nature of our project. The definition of our project was : project, begin, demo, evaluate, suggestions, program, review, question happy, and until. So until he was happy, we would begin and loop through the process again. So this concludes the formal part of our journey. We've seen that we've used Forth entirely through this process. We started out with the simplest of one board processors. We went through our homemade development systems. At this time, development systems cost around $6,000, $5,000. In today's money, that's roughly $15,000 to $20,000. It was a financial burden to have done that. We probably could have spent that money, but again, the interactivity was totally not there. These classic development systems went from floppy to floppy. You would burn proms, you code, edit code, burn a prom, put the prom in the product, didn't work, edit, assemble, burn another prom, and so on. In all of these projects that we talked about, the product itself was umbilically connected to a Forth development system, but we literally could go into the product and look at RAM, input, output, the data results from activities. So we all know the interactivity. this was our secret weapon. When Honeywell would come visit our plant, we would go into our library and take the fourth books and turn them edge down so you couldn't read the title. So when you walked by, because we didn't want Honeywell to know why we were getting the results that we were. So after the saga of this major hunting expedition, we now go into recreational shooting. The ammunition and weapons I was using then would be Win-32 4th by Andrew McEwen and Tom Zimmer, which was begun in 1995. It was actually begun earlier than that, begun in the mid 80s. Andrew McEwen started this at Dorado Systems as a little private moonlight project. He carried it on as Windows 3.2 came out, and he brought essentially 483 through a couple of generations, added in ANSI compliance, and then interfaced it very elegantly to the early Windows. His work concluded with Tom Zimmer in about 2003. And at that point, a European team took the project up and continued to update it to match Windows as Windows evolved. And the project has been pretty well frozen since about 2012. Some updates have been done through then, mainly user interface. It's essentially ANSI compliant. As far as I know, the ANSI standard hadn't quite been accepted by then, but it appears that the European team has brought it into compliance. And to me, to my thinking, the nice part about this is that it is a frozen system. That is, the originators are no longer making any changes to it. We all have fourth systems that we change ourselves. A lot of times documentation is not generated because it's a moving target. In this case, we have a frozen system, so it is much easier to document. In reaching Win-32 4th, I came into it, of course, from a fourth world, an assembly world, a block world, no files. And so the newer concepts came along in fourth, primarily driven by the industry practice being reflected by the ANSI standards work. And of course, I know the concepts, but I had not had personal use of many, many of these constructs. So I came in as a new user, a starry-eyed new user for things like catch and throw. I would go to the ANSI documentation and read it, and it was incomprehensible because the ANSI documentation is not written as a user guide, it's written as an implementer guide. So it's written in implementees, technical jargon, not how you use it, but it's what its structure is. So I had to go back to the Win-32 4th, which fortunately is all source is available, and it is lightly commented. The machine code part is poorly commented. The high level is moderately commented. And so I've had to go back and reconstruct and relearn all these. And as I did it, I would then take notes. The notes kept growing and growing and growing, and that has grown into the book we'll see in a few moments. The innovations that came along in Win-32 4th are such things as the ANSI standard catch and throw. Andrew came out with there are some 12,000 words in Win-32 4th, I believe. To keep dictionary searches fast, he uses a 257-way hashed thread. So compilation is extremely fast because the lookups are done by a 257-way hash. There are words such as the conditional completion, if, else, then, standard messages. To me, floating point and the floating stack was a new world. And of course, it's got all the trig and transcendentals built in. Newer words like defer and postpone. There's a major component, which is object-oriented programming, which I still have not gotten to at all. Execution change. It uses the heap memory management from Windows. So the very early simple bank switching methods that older fourth used now are set aside, and it goes directly using the resources provided by Windows, and it's apparently compatible from everything from XP to the current Windows 10. There's a lot of tools built in. If Andrew needed a function, rather than putting it as an accessory to load, he just built in the system. So it has ever so much support built in, words like see, view, and debug, which will disassemble from memory. You type view and to a word, and you will be taken directly to its source code. And debug allows you to do single stepping or essentially breakpointing and code. Very simple way. Well, all of this went into a Word document, which is still under development. And now we'll take a look at that guide. Now, I hope this is readable on your screen. Because of bandwidth, I think it might come out a little bit fuzzy. And so I've enlarged the screen here, and we may hold this a little bit briefer just because it's a little bit on the difficult side to read. Yeah, actually, that was pretty good. This is an Adobe Acrobat version from a Word original, and it uses the linkage. So if I want to look at the bit of fourth history, I just hit Control, click, takes me to each section. So here's a little history on how I got involved with fourth and the development done with Robert Seltzer, how Fig Fourth came along. We go into the history of WinForth, how it came along, what its growth was like. This is a section on the improvements that were made in the last 20 years by the European team. Generalized fourth documentation, how to get started, where to find resources. And now we get to writing your first fourth program, and we tell a newcomer how to program Hello World. It's obligatory for all new programmers to start with Hello World. We then indicate how to interact with the text interpreter. Basically, it's going to tell people when you input to the keyboard what this fourth system is going to do in response. And of course, we know it's going to either execute words or numbers. There are two editors in 132.4. One is just a pure file editor, and then the second one is the integrated development environment that came along later. And by all means, one should use the integrated development environment. It has been brought up to date by adding the scroll wheel, which was not in the originals, which makes a big, big difference. To get started, we tell people here are some words to try right from the keyboard. It'll show you what the resources are available inside your system. And then now we go through the fourth basics, like what is the stack? How are words represented? Stack manipulation, dupe, drop, overswap. This is an introduction, but it also documents the words that are present in the system. We go into defining words, constants, values, variables. Again, nothing new here, but this does capture exactly what's in the system and how it can be utilized. We get into conditionals, if then else, do loop, case statements. Again, documenting what fourth is like and how the system responds. The Win32.4 has a rich variety of memory access. We can access memory on a byte basis, on a word basis, on an 8-bit byte, a 16-bit word, or a 32-bit cell. It is fundamentally a 32-bit system. With double words, it's a 64-bit integer system. There are a large number of input formats. These are all the double number operations. And again, Andrew put in a very rich selection of words going clear up to things like 4-dupe and 4-drop and 3-dupe and 3-drop. So words that normally you would write within an application are resident in the system. This is the basics of the floating point operations. It's a quick overview on what it will do. I don't take all the words and explain every single word. So when we get into things like transcendentals, we just give you a list of them, and that's what is capable within the system. At the systems level, I capture the documentation for the floating point. It isn't too likely that people were going to be needing this, but I wanted to document it again for my own understanding. So this is the basis of representations within the system following the IEEE standard. Again, here are outputs. You can output bytes, you can output cells, you can do write justified, you can do hex outputs, you can do octal output, a very rich selection of numeric output. We'll go through. Now, there's a section on programming technique. This is more on the tools that are used, things like file interaction to include, fload, require, so on. This area was new to me because I had not done file-based programming, so I was doing the learning here right along with the newcomer. Again, more support on files. Commenting. These are vocabulary support and dictionary support with things like words, see, view. Forget. The forget is a smart forget, so it will forget across vocabularies. And if new type words have been added, it will find all additions to the dictionary at a forget point. So it's a very forgiving forget structure. These are the Windows keyboard shortcuts. There are about 100 of them, many, many more than I would ever know, remember, or utilize. But look at all the keyboard shortcuts that are inherently built in the system. There we go. String support, very rich. ANS4 has codified that, and it works out extremely well. We'll skip ahead here. We get down into the dictionary word structure. Again, a rich selection of words so that you can find code fields with tick. You can go to the parameter field with toBody and then move around from field to field to field. You're doing system level programming, you're writing error routines. This comes in very, very handy. Of course, it has create, does, and semicolon code. These are explained in different degrees of detail in other systems, and I try to bring down the useful component here. Commenting, and again, let's see. Back to floating point. This is the in-depth use of floating point operations. I note repeatedly that this is a work in process. There are sections of this where you'll see notation that says to be completed, or fix this, or check this. This is not a finished product. It never will be. It's a dynamic process in process. There's a whole section on using the assembler and assembly level code. Lots of examples. ANSI system has a number of standard messages. These are all included. It's part of catch and throw. And I found out you can, this is extensible. You can add your own messages to it. It's undocumented, but it's built in the system. And so now within my report here, it is now documented. And now we're down to the object-oriented programming portion, which we will skip over. But there is about 12 or 15 pages on the object-oriented portion, because all of the high-level user interface, the IDE, is all done with object-oriented programming. And finally, we end up with some of the fourth internal details, how things are done internally. So that, let's see, let's get to, the reference slide. So here's our credits to wind up. As we said, Andrew and Tom Zimmer did Win32 Fourth. The European team updated it, and it has then built to, I want to thank also the effort of all the fourth fanciers around the world who have added to the richness of the language and the standards work. This manual is posted at GitHub under my name, Bill Ragsdale, under Win32 Fourth Guide. So thank you for your rapt attention, and we will now turn it back to our fearless leader.
Unmute. I'm unmuted. I guess on Meetup, I'm called the organizer, and my assertion on Meetup is that organizer may be too strong a word. But in any case, thank you, Bill. That was great. And you'll notice, those of you watching, that in the chat, I've posted a link to Bill Ragsdale's Win32 Fourth Guide on GitHub. Maybe Bill will have a look at that and tell me it's the correct one. It is just one of a number of things that are out on the internet to help you learn about and understand the history of and move forward with. And I'll be talking about that a little later in the show. But if you've got some particular link to something interesting about Fourth that's out on the web that you are particularly excited to share, I'll give you a little time while others are speaking to maybe dig up that link and have it available for us later on when we start talking about this stuff. Moving on, Ting, are you?
I got a couple of questions, Bill, about Win Fourth. One, can you give any details about how the heat management is handled? Because that's to me one of the really issues in bringing Fourth to the level of higher level languages. And the other thing, are the objects dynamic? I mean, can you create and destroy objects at will, if you will?
I'm smiling because when you hit a sensitive topic, then I smile. As I said, I'm learning this. I've used this system for off and on, casually, maybe 8 years. Picking here and picking there, little projects. The last year, what with COVID lockdown, I'm using it a lot more. However, I've only recently gotten involved in actually using and creating files. Of course, we edit files and use them for source code, but I'm using them now in applications where I'm using data logging into files. I have just gotten to the heap function. Now, the heap function is a very clear, clean implementation using the resources of Windows. So there's malloc, which goes to Windows and grabs a memory area, and you identify it by my understanding is by its base address. So its base address becomes its identifier, and you can add, you can expand, and you can release memory allocations at the size you wish to the resource level of your computer.
That really answers my main question, because one of the things that I punt is when I get down to creating or freeing an object, a list, I just punt it out to the operating system, create and destroy. That's one of those issues where Arthur Whitney has a very fast inventory system that never moves data. There's never any garbage collection. And that's what would be implemented on any fourth where you've got total control over some address space. So that really was my main thing. So you can create and destroy objects because you've got essentially the allocate and free that the operating system has.
A huge contribution Andrew made, and Tom, was by decoding, decrypting the interface to Windows. There are some 6,000 window calls by name buried in the system. Somewhere there's a vocabulary that has 6,000 window calls value and the calling sequence. So things like the access to the Windows multitasker is there. So when you multitask in Win32 it's no longer the round robin that is inherent in a normal fourth system, but it's the interrupt driven or time driven managed by the Windows system. So chunks of Win32 could disappear because they were transferred over to the operating system. And to me, that's of course, and the other thing too that they've done is this fourth is in a virtual address space. So you have, I'm not even sure how big it is, but 50 megabytes or so, 100 megabytes of dictionary space, and it resides from the number 0 to some large number in its own virtual world inside the Windows system. And every time you make an access to a fourth address cell, underneath that is a translation to the Windows equivalent. And then when a value comes back, that value back is translated again from the Windows world to the fourth world. So underneath all of this, transparently, you don't see, there is this two-way address translation to and from Windows. The tool words are available, and if you had total nerve and skill, you could end up talking directly to RAM of your host computer. All of that is a light year above the skill level and interest level that I have. That's it. On the object-oriented programming, all the high-level stuff like the editing, the user interfaces, the diagnostics is all done at object-level programming, and that's an area that I am lightly familiar with, and that's as far as I can go. I have very light familiarity. However, Andrew put down about a 12-page summary of this. It's based on the system called Neon, which I think was fourth-based. And so it's at least, I've copied 12 pages of Andrew's notes into my book. Okay?
Thanks.
Ping?
Yeah, Bill. Yeah, it's good to see all the history behind the Fig Forth. Yeah, I was always wondering what was the prototype of Fig Forth look like. I think it was on your 6502 system and mostly in blocks, I think. And then you take the code in blocks and then get the Forth implementation team to translate them into assembly for many other systems. So I think, is it true that your original Fig Forth is on your 6502 system in blocks?
Oh, absolutely. Yes.
Yeah.
And the original was 2 block buffers. So we had 2 1K blocks in memory. Let's see. I think the original had, the blocks were in RAM, and we had something like 10 or 20 blocks, and the buffers was 2 sectors. The sectors were 256, and we had 2 sector buffers, so that if you flushed a block, you actually had to write 4 sectors to be able to flush 1 block. And so the original development work was all done RAM to RAM from paper tape. So paper tape would load in, we'd load the code in blocks, we'd go into RAM, we'd do development work and come out and punch paper tape. Then miraculously, of course, we went to the PerSci floppy disk drives, and the whole world got much brighter once we got to floppy disks and an ADM3 terminal. But the thing was bootstrapped up. It was bootstrapped up from assembler, and then literally through writing next, and then writing a couple of words, and then watching a couple like a push and pop and next, and bootstrapped up, 2 or 3 words at a time, all at the hex level. They were all done, looking at a teletype, doing hex dumps. And then at one magical point, this proto system, this tooth, what I call tooth, it actually output a line of text on the teletype. It actually outputted some usable output that was not a hex dump. And then at that point, I knew I had something that was working.
Very good. Yeah, how long was the Forth implementation team working to bring up those Fig Forth systems?
It was about 3 months. We would meet, if I remember right, we met every 3rd week, either every other week or every 3rd week. We met at the Southland Shopping Center at a food court, and they had a side room. So we'd eat and code. And so each session, I would bring about 2 pages of code. And if I remember right, I would bring in the 6502 assembly listing, not the high-level Forth, but literally the assembly listing. And we would take about 3 or 4 or 5 words and explain the logic to them, how the stacks worked, how next worked. And then the teams would go ahead, about 9 people would come, and each had their own processor. And then they would go away and they would code those 4 or 5 words and understand the theory of what they were doing. And then we'd get back again 2 weeks later, and they would take it another pass. And it took about somewhere less than 3 months, somewhere in the range of 2 months to 3 months. And the result then was that each one of them had an assembler for their particular system. And so when they were done, they would have Forth written in assembler from top to bottom that would assemble and run. And those were then published as the FIG listings. And we began to provide them to the FIG membership. And at the West Coast Computer Fairs, the place, they went crazy when those listings started showing up. And of course, our poster child is Dwight Elvey, because he went to the West Coast Computer Fair, got the 8080 listing, got it on Saturday, took it home, typed it in. He and his wife typed nonstop until Sunday afternoon. And then by Sunday evening, he had it assembled and running. And he called us back on Sunday night or Monday morning saying, I got it running. And so that was the milestone. Thank you, Dwight Elvey.
Yeah, that was in the summer of 1978, right? Yeah, thank you. Yeah, that was great work in documenting the Win32 Yeah, I just gave up. Okay, it was too complicated.
Well, the advantage was that we had, each person knew their host computer processor well. And people like Gary Feuerbach, he did something, I forget what, but it was a computer nobody had. He was the only one because he had access to one at work, I guess. And so another guy did the TI 9900. And so the breadth of the processors was quite amazing.
Yeah. Thank you.
We had a guy who actually sent in a listing from the CDC, what, 6600, one of the CDC supercomputers. And he had done something like along the line of what you're doing using C. He had taken some language that was on that computer and he had written a Forth emulator that actually kind of ran Forth. And for example, he had a word called trash, and to drop something, he would store to trash, but to duplicate, he would store to trash, and then he would recover from trash. So he would go trash store, trash fetch, and that was a duplicate. So he even bootstrapped up fetch and store. Anyway, enough on that. Enough on that.
So while Ting has his mic unmuted,
Okay.
we'll get on to our next presentation, Java bytecode review.
Okay, thank you. Thank you. Let me just grab the shared screen. Share sound. Okay, let me see if, yeah, you see my screen.
We see a sign that says Ting has started screen sharing.
Hello?
We see a sign that says you started screen sharing.
Oh, yeah, you are screen sharing? Yes.
It's just back.
Okay. Okay, let me see if I can change these things. Oh, I don't seem to have the full control of my computer. Okay, you are timeshare. Okay, okay. Yeah, it's very sluggish.